So what I want you to do is look at this structure. I want you to tell me the number of signals you expect for the structure. Just like we did before, identify your protons in alphabetical order from left to right. That will help both of us be consistent in our identification. Once you've identified the number of signals you expect in your NMR, look at each of the sets of protons. What do you expect for the integration, the chemical shift, and the multiplicity? So pause the video, identify the number of signals, and then the integration, chemical shift, and multiplicity for each set of protons. So in my NMR for this molecule, I would expect 3 signals, and I've labeled my protons as HA, HB, and HC. I'm going to start with HA. In the protons that I have identified as HA, I am expecting to see an integration to reflect the number of protons at that position. So I have 3 protons that I've called HA. I would expect my integration to be 3. I am expecting a chemical shift for these protons. That's going to be in the alkyl region, so a chemical shift of about 1. And I'm expecting a multiplicity based on the fact that my protons HA see 2 protons on the adjacent carbon. So that's going to give me 2 plus 1, which is 3. So I'm expecting a triplet for their signal. If I look next at HB, the integration that I would expect for HB is going to tell me that I have 2 protons that I have identified as HB, so I'll have an integration of 2. These protons are alpha to a carbonyl, so I'm going to expect a chemical shift of about 2. For the multiplicity, I need to look at my adjacent carbons. This is one adjacent carbon for my HB protons. This is my other adjacent carbon for my HB protons. This adjacent carbon has 3 protons, which we have previously identified as HA. This adjacent carbon is not bonded to any hydrogens. So HA will be how the signal for HB is split. And so my multiplicity is then going to be 3 plus 1, which is 4, and my signal will be a quartet. For my protons that I have identified as HC, there are 3 protons that I have identified as HC, so I would expect an integration of 3. When it comes to the chemical shift for HC, these are protons that are bonded to a carbon that's also bonded to an oxygen. So that means that these protons are going to fall in the range of being alpha to an electronegative atom. So that means that these protons are going to fall between about 2.5 and 4.5. So I'm going to identify my chemical shift as being between about 3 and 4. Usually protons that are bonded to a carbon that also has an oxygen fall right around 4. Finally, for the multiplicity, I have 3 protons that I've identified as HC, and my adjacent atom is an oxygen. My oxygen has no bonds to hydrogens, and so I have 0 protons on my adjacent atom. So my multiplicity is going to be 0 plus 1, which is 1, making my peak a singlet. So in the spectrum for this molecule, I am expecting the signal for HA to have an integration of 3, a chemical shift of about 1, and a multiplicity of a triplet. For HB, an integration of 2, a chemical shift around 2, and a multiplicity of a quartet. And for HC, I am expecting an integration of 3, a chemical shift between 3 and 4, and a multiplicity of a singlet. So as I look at the actual spectrum for this molecule, Here I have the structure with my protons A, B, and C labeled. When we look at the data in the spectrum, we see 3 peaks, which is consistent with what we expect. For the protons that I've labeled HA, I said that I was expecting an integration of 3, and so I have 2 peaks that integrate for 3. But for HA, I was also expecting a chemical shift of about 1 and a multiplicity of a triplet. So right here in the data, right around 1, I have a triplet. So this peak here is the protons for HA. So this peak here is a triplet, has an integration of 3, and a chemical shift of about 1. This is consistent with what I expected for HA. For HB, I'm expecting an integration of 2. I'm expecting a multiplicity of a quartet and a chemical shift around 2. And I see that all of that consistent with what I'm expecting here for this peak. So this is the peak that's consistent with HB. That leaves HC. So this will be the peak for HC. I'm expecting an integration of 3, a chemical shift between about 3 and 4, and a multiplicity of a singlet. So that all of the data that we expected is what we see in this spectrum. As we continue to work through NMR problems, there's 2 ways that you could be asked problems. You could be given a structure and asked to make predictions about the spectrum based on what we know. You could also be given the spectrum and a chemical formula and asked to go back to the structure for the molecule. When you're given the data and the chemical formula, what you're going to do is begin by proposing structures that are consistent with the chemical formula, making predictions just like we've done here, and seeing if the data matches the predictions that you have made. You now have enough information to complete the in-class activity that asks you to make predictions about the NMR spectra for 8 different molecules. As you begin your study of NMR, the first thing you need to focus on is understanding why spectra look the way that they do. That is to take a structure and make predictions about the spectrum from the structure. Because as we continue into spectral analysis, we're going to be proposing structures and seeing if our structures fit the data.